In the earlier class, we have introduced channel coding and also learnt what is a block code. So, a block code is defined as follows. The notation used is n comma k. A block of k message digits is mapped to a larger block of n code word digits, and the digits are chosen from a given alphabets of elements. Now, for our study, we will restrict to binary code. So, in that case, we will have k bit messages which form 2 raised to k message sequence, also known as k tuples, and we will have n bit blocks which will form 2 raised to n distinct sequences referred to as n tuples. So, the job of the encoder is to take each of these 2 raised to k messages and assign one of the 2 raised to n tuples. So, here we will have message sequences which are k bit long, and here we will have the code words which are n bits long. So, what we get is that 2 raised to k messages, k tuples, uniquely get mapped to 2 raised to k code word n tuples. Now, before we proceed ahead, we need some concepts from vector spaces and subspaces. So, let us define the vector space. The set of all binary n tuples, which is denoted by this curly bracket, and this n denotes that we are talking about n tuples, is called a vector space over the binary field of 2 elements 0 and 1. So, binary field has 2 operations, addition and multiplication, such that the results of all operations are in the same set of 2 elements, that is 0 and 1. So, arithmetic operations of addition and multiplications are defined by the conventions of the algebraic field, and which for binary field are as follows. Addition is given by this rule, multiplication is given by this rule. So, we see that this is an exclusive OR operation and this is a AND operation in Boolean terms. So, now let us define a subspace of a vector space. A subset S of the vector space is called a subspace if the following 2 conditions are satisfied. The all 0 vector is in S and the sum of any 2 vectors in S is also in S. This is known as a closure property. Now, we see why we require all 0 vector, because if this condition has to be satisfied, then I can choose two vectors to be the same vectors. So, when you take the same vectors and if you add them using the rules of addition just discussed, we will find we will get a 0 vector, and by definition we require that the summation of these two vectors should be in S, and therefore we see the need for the all 0 vector in S. Okay. Having defined this, we will study a special class of block code that is known as linear block code. So, the definition of the linear block code is as follows. Let Vi and Vj be two code words. Remember, this Vi and Vj, they correspond to two different message sequences, say Mi and Mj respectively. Now, if we have these two code words, which will be, each of this will be n tuple, and it comes from the binary block code, then the code is said to be linear if and only if Vi summed by Vj is also a code word in the same nk binary block code. If this condition is satisfied for any block code, then we say that that block code is a linear block code. An example of that would be, let us consider a vector space V4, so which denotes that there will be 2 raised to 4 16 4 tuples, right? The length of the each of the vector here is 4 bits, and these are all 4 bit vectors which we can form. Now, a subspace of this is chosen by these vectors, and it is easy to verify that these 4 vectors satisfy the definition of subspace. So, first of all 0 vector is included in this subset of V4, and next, if we take the summation of any two vectors, we will get a vector which lies in the subspace. So, based on this definition of linear block code and a subspace, we can say that a set of 2 raised to k n tuples is called a linear block code if and only if it is a subspace of the vector space Vn of all n tuples. Okay? So, this can be actually visualized with the help of this figure here. So, imagine the vector space Vn which comprises of 2 raised to n tuples. So, within this vector space there exists a subset of 2 raised to k n tuples which make up a subspace. Now, this 2 raised to k vectors or points are shown here among the 2 raised to n points, and this bigger dots represent the code word of this subspace. So, a message is encoded into any one of the 2 raised to k allowable code vectors and then transmitted. Now, because of noise on the channel, a perturbed version of the code word, which will be one of the other 2 raised to n vectors in the n tuple space, will be received. Now, if the perturbed vector is not too dissimilar from the valid code word, the decoder will be able to decode the message correctly. So, the basic goal in choosing a particular code is similar to the goals in selecting a set of modulation waveforms, and this goal can be stated as follows. We want to choose 2 raised to k n tuple subspace of code words from this entire space in such a way that we get the coding efficiency by packing the entire space with as many code words as possible. So, what we are indirectly saying that we want to have small amount of redundancy, which implies that we do not require excess bandwidth. And the second condition is that we want these code words to be selected in such a way that they are as far apart from one another as possible, so that even if the vectors experience some kind of corruption during transmission, they may still be correctly decoded with a high probability. Now, an example of 6-3 linear code is given here. So, we have message sequence of 3 bits. So, there are 8 messages, and corresponding to these 8 messages we have 6 tuples, and we can see that we will have 2 raised to 6, that is 64 n tuples, 6 tuples that is, and out of that we have chosen 6 tuples in such a way that it forms a subspace and it forms a linear block code. Now, suppose example, instead of 6, 3, if I had 127, 92 block code. Now, in that case I would have 2 raised to 92 code words or code vectors. Now, obviously the job of the encoder is to assign one code word to each of the message vector. Now, does this imply that we will have to set up some kind of a table lookup type of thing? And if we assume table lookup, then obviously in this case it will fail, because the requirement would be very huge and implementation will not be practical. So, let us look at a feasible implementation of a linear block code. Observe that linear block code is a k dimensional subspace of the n dimensional binary vector space, where k is less than n. This is the definition of a linear block code. So, what this implies, that it should be always possible to find a set of k n tuple vectors which are obviously fewer than 2 raised to k n tuples, that can generate all the 2 raised to k n tuples code words. So, this generating set of k n tuple vectors is set to span the subspace, and the smallest linearly independent set that spans the subspace is called a basis of the subspace, and the number of vectors in this basis set is the dimension of the subspace. So, any basis of k linearly independent n tuples can be used to generate the required linear block code vectors. So, we can conclude. So, what this means, that each code word which I denote by UI, the capital U denotes a code word and also a vector, a row vector. So, this can be written as follows: UI is equal to M1, which is the first bit of the message sequence multiplied by the vector V1 plus M2 times V2. So, remember this V1, V2, Vj are all vectors, whereas M1, M2, Mj are the scalars, and M1, M2, Mj are the components of the message vector which is formed out of the message sequence. So, your Mj is going to be 0 or 1 and your I will be from 1 to up to k, because the dimension of the subspace representing the linear block code is k. So, we can in general write this in a matrix form as follows. So, first we define what is known as a generator matrix of the size k by n, and there are k rows and n elements. K rows corresponding to the k independent vectors which form the basis of the subspace, that is why k, and each of this vector has n components because the code vectors are n tuples, and the vector elements for the code vector V1 are V11, V12 up to V1n, and similarly the components of the code vector Vk are Vk1, Vk2, Vkn. So, these code vectors, they form the rows of this generator matrix. So, now this equation which we have written is equivalent to writing in matrix form using the definition of generator matrix as follows. So, message vectors are the message bits M1 to Mk, it is a row vector, and the corresponding code vector or code word generated by the encoder is denoted as u. So, that u would be equal to, this is a row vector multiplied by the generator matrix, and this is equivalent to this. Here this is corresponding to the code word is corresponding to the message mi. So, this is a message mi. So, this is a vector, remember this is a vector here, right? Okay. So, for the earlier example which we had studied, we can obtain the generator matrix as follows. Generator matrix is given by this, and we can see whether this produces the code words as expected. So, if you take the message vector to be 1 1 0 and take this V1, V2 and V3, right, and generate it using this equation, we get the output to be equal to this, and you can check that this is identical to what we had got earlier. Now, if you look at the 6.3 code word which we studied as an example here, it has some kind of a characteristic, and the characteristic is as follows. If you look at this message vectors out here and if you look at the code words, we see that these 3 message bits, they appear at the end of the code word here. Similarly, if you see this, it appears at the end of the code word here, and similarly 0 1 0, it appears at the end of the code word here, and this is true for all the message vectors and the corresponding code words. Now, this kind of a linear block code is what is known as systematic linear block code. So, what is a systematic linear block code? It is a linear block code and it is a mapping from a k dimensional message vector to an n dimensional code word in such a way that part of the sequence generated coincides with the k message digits. In our case, k message bits, because we are talking about a binary code, and the remaining n minus k digits are parity digits. So, a systematic linear block code will have a generator matrix of the following form. So, the generator matrix G is partitioned into two submatrices. This is known as P array and this is the identity matrix. So, parity array is of the size k by n minus k, whereas the identity matrix is of the size k by k. And the elements of this generator matrix are given as shown here. So, this corresponds to the parity array and this corresponds to the identity matrix, where the elements Pij is either 0 or 1. Now, given this, for a message specified by this row vector, the code word u, which has the elements from u1 to un, u will be obtained by the usual matrix multiplication of the row vector corresponding to the message vector multiplied by the G generator matrix, and any of the element of this code vector or code word u, say ui, is given by this expression on the right hand side. So, this is ui will be given by this term for I equal to 1 to up to n minus k, whereas for I equal to n minus k plus 1 up to n will be the same as the message bits, because this is a systematic linear code. Now, this vector code word vector, which is given in the terms of the elements ui, it is also expressed in a different manner, and the first n elements of this code word or code vector are also known as parity bits, and rest of the elements or components in this vector are the message bits, because we are discussing the systematic linear code. So, these parity bits are obtained as shown on this slide. So, this parity bits P1 to Pn minus k are exactly the same as the first n minus k elements or components of the vector u. So, let us take a earlier example and obtain the code word for any general message m. So, we take the example 6,3 code, for which the generator matrix is given as shown here, and the code word for any message vector would be obtained as shown here. So, this example shows how the parity bits are obtained by linear combinations of the message bits. So, this parity bits in fact provide the ability for error correction and error detection. We will continue with our study of linear block code and see basically how to detect the errors and correct the errors. So, we will define the notion of what is known as parity check matrix, and this we will do in the next class. Thank you.